So this is just 2 questions in your homework. I will prepare the homework and upload it in Hour2 class. But if you just want to go ahead and start today, just to show that if you have 2 operators, the matrix representation of the product is nothing but the product of the matrix representations. This is your homework 1. Now homework 2, we had already defined what we call the Hermitian conjugate of an operator. Just show that the Hermitian conjugate of an operator has the matrix representation that can be obtained by the matrix representation of the operator itself, not its Hermitian conjugate. You take the matrix representation of the operator, take its complex conjugate, and then transpose it. Now let's try to combine these a bit. So we have many kind of apparently independent things. So let's try to combine them, and eventually we will just relate it to the physical description that we are looking for. Now first, let's say we have this Hermitian operator. Can you close the door also? Now we have this Hermitian operator. Let's assume we have found a basis, an orthonormal basis, made up of the eigenkets of this Hermitian operator, such that h of alpha I is equal to alpha I times the ket, and alpha I, alpha j is equal to Kronecker delta ij. We know that given a Hermitian operator, we had already discussed that we can always find an orthonormal basis made up of the eigenkets of this operator. Now the question is, what is the corresponding operator? We can talk about the matrix elements, or we can in fact just straight away write down the operator. Let's start with the matrix elements of this operator. This is H alpha I, alpha j. This is one matrix element. This will be equal to, well, since alpha I is already an eigenket, this is nothing but alpha j times alpha I, alpha I. Well, alpha I is just a number. I can take it out of this inner product. Alpha I, alpha j, alpha I. Well, this is an orthonormal basis. So this alpha j, h alpha I, well, this is nothing but Kronecker delta ij. This is equal to alpha I, Kronecker delta ij. As a matrix representation, we said that this we can write as hji. So the element of the matrix corresponding to H at the jth column and jth row, ith column is 0 if the column number and the row number, they are different, and it is equal to alpha I if the row and the column number are the same. Here? No. Alpha I is a complex number in general. No, I don't need to take the complex conjugate. You see? No, there's no complex conjugation there. Now, the numbers, I can just take it out. But you see, keep this in mind. If we define a state gamma, let's say A alpha plus B beta, then this gamma is equal to A conjugate bra of alpha plus B conjugate the bra of beta. The only conjugation we have is over here, but not in the inner products. I can always take the numbers out of the inner products without doing anything. This beta multiplied the inner product with gamma will always be A times beta alpha plus B times beta beta. So we always said that if you have an operator, its matrix representation will depend on which basis you choose. If you choose a different basis, the numbers will be different. Just like if you have a vector, its components will be different if you choose different axes, and you're always free to choose your axis. But once you choose your basis as the collection of the eigenkets of your operator, then the matrix representation of that operator is always diagonal. So this is basically what we had proven over here. So if you want to write the matrix representation of H, this is just alpha 1, alpha 2, etc., and all zeros everywhere else. This Kronecker delta tells me that the matrix elements are non-zero only if the row index and the column index are the same. But when the row index and the column index are the same, we are talking about the diagonal elements. But you see, even if we have degeneracy, we had said that we can always choose an orthonormal basis made up of the eigenstates. So that is where I started with. I mean, if you want to talk about the matrix representation of any operator, first you have to specify what your basis is. Because if you choose a different basis, it will look completely different. For example, she can choose one basis, you can choose another basis, you will obtain completely different matrix representations, but they can still be the same operator. So if you want to compare your operators, you have to first make sure that you have your identical basis, and then you can compare the matrix representation. So first I choose my basis. So here I made that choice. I have my operator, I can talk about the eigenkets, I can normalize them, and I can always choose an orthonormal set that forms my basis. So I started with an orthonormal basis. In that basis, my matrix representation of the operator is diagonal. Of course, if I have degeneracy, not all the eigenkets, they won't be orthogonal to each other. But to simplify my life, I would rather choose an orthonormal basis. In that case, I have a choice and I'm making that choice. Only if I make that choice, my matrix is diagonal. Otherwise, as you said, it won't be diagonal. But I'm choosing, in the case of degeneracy, I'm choosing, and if there is no degeneracy, there is no choice anyway, I'm choosing an orthonormal basis to start with, to work with, to make my life easier.
Hocam bu ortadan aklımda aynı şekilde en var yılları da oluyor değil mi? Marx'ın en yuvarlarını bulup o en yuvarlarını şekilde yazabiliyoruz.
And
en yuvarlarını.
eigenvalue.
Bir Marx'ı kompleks bir Marx'ı basitleştirebiliyoruz ya.
Now that's basically what I'm doing. H, in an arbitrary basis, will have a complex representation. But I'm choosing a special basis which is formed by the eigenvectors. And in this basis, it takes a lot simpler form. It's a diagonal matrix whose diagonal entries are the eigenvalues. So once I know the eigenvectors and eigenvalues, I can obtain a diagonal matrix representing my operator. So this is quite a simple matrix. Let me look at another operator. Let me call it, for the time being, H prime. Alpha I, alpha I, alpha I. Let me look at this matrix. This is not a matrix, this is an operator. or this summation index, let me use K. And let me look at the elements of the matrix representing this operator. This is alpha j, sum over this time k, alpha k, alpha k, alpha k, multiply with alpha I. This is equal to sum over k, alpha k. Now this alpha k is just a number. It's the eigenvalue. And I'm using this eigenvalue just to name my kets. Alpha j, alpha k, alpha k, alpha I. Well, I'm still working on an orthonormal basis. This is where the simplifications come into the game. This is Kronecker delta jk, and this is Kronecker delta ki. Now I can just use the first Kronecker delta to take the summation over k. That tells me that only the k is equal to j term gives a non-zero contribution, and the k is equal to j term is alpha j Kronecker delta ji. But basically this tells me that alpha j a prime alpha I is equal to alpha j h alpha I. So these two operators, the first operator, I don't really know what it is. But I know that it has I can choose an orthonormal basis. I choose that orthonormal basis. And I know its eigenvalues. And in that basis, H has this matrix representation. Well, in the same basis, this H prime operator I defined also has the same representation. And since I'm basically using the same basis to represent both of them, this tells me that these two operators are the same thing. So H, I don't know what it is, but I can, once I define, let's say, its eigenkets, and that have eigenvalues alpha I can show that operator in this form. This is my operator. Well, I can also use this for the identity operator, if you want. Well, identity operator is highly degenerate, but nevertheless, even if we have degeneracy, we can always choose a basis that is orthonormal, that is made up of the eigenvalues, eigenkets, sorry. And in that basis, what are the eigenvalues of the identity operator? Now, what are the eigenvalues of the identity? 1. They're all 1. Whichever ket you act on with the identity operator, it gives you 1 times the same ket. So all the eigenvalues are 1. So just using this general prescription, let's say, our prescription is you have your Hermitian operator, define its eigenkets, find its eigenvalues, and in using those kets and the corresponding bras, you can define your operator as that sum. In case of the identity operator, alpha I, they are all 1. So this is our identity operator. Now let's look at our SZ operator. Now, how do we should first define this S-set operator. What do we exactly really mean by the S-set operator? Now, we had seen that if we have a Stern-Gerlach apparatus with magnetic field in the Z direction, when we send a beam of silver atoms, they are split into two. One goes above, the other one goes below. And it turns out that they have different magnetic dipole moments, which differ in sign. And we assign this magnetic dipole moment to a property that we call the spin. Well, we will define it also later on. So we have these two states, the plus states and the minus states. Well, the plus states has spin plus h bar over 2, and the minus states have spin minus h bar over 2. So we know this S-set operator. We know that it has two eigenvalues. One is plus h bar over 2, the other one is minus h bar over 2. So the S-set operator I can write as h bar over 2 plus 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 minus h bar over 2 minus minus. Now these plus minus states, we define them to be orthonormal. Plus plus is equal to minus minus is equal to 1. And plus minus this is equal to 0. Well, we can also show this as a matrix. We had just seen that these kets we can show them as column matrices. Now you see this plus state is 1 times plus plus 0 times minus. So these numbers 1 and 0, it uniquely describes my ket, and I can just organize them as a column. Well, usually the eigenvalue that has the largest value starts from the top element, and the lowest value is the lowest element. So this is we have two eigenvalues, plus 1 and minus 1, up to h bar over 2. So the plus state, we just show it as the 1, 0 state, and the minus state it has 0 plus plus 1 minus. This is the 0, 1 state. Now this plus minus, plus plus, sorry. We can show it as a matrix. Well, rather than calculating the matrix elements directly, you see this is just a product of a ket and the bra. To obtain the corresponding matrix representation, just multiply the matrix representation of the ket with the matrix representation of the bra in that order. So this will be equal to, well, the ket is 1, 0. The bra, well, to obtain the bra from the ket, that is in turn to convert the matrix representation, take the complex conjugate and the transpose, which is 1, 0. Well, this product just gives you a 2 by 2 matrix. This is equal to, well, let's see, 1 times 1. This is this element that is 1. 1 times 0, it is this matrix, this element. 0 times 1, 0. 0 times 0, that is 0. This is the plus ket multiplied with the plus bra, the corresponding matrix representation. And similarly, we can do the same thing for the minus. This is 0, 1, 0, 1, which is equal to 0, 0, 0, 1. And so we can just write the SZ. This was equal to h bar over 2 plus plus minus h bar over 2 minus minus. And this has the matrix representation, h bar over 2, 1, minus 1, 0, 0. So we know the matrix representation of SZ now. It is this minus sign over here. The eigenvalue is minus. Well, it's not easy to make experiments with electrons. They have a charge, they are attracted to everything around them. They made the experiment, I had found the experiment also with the hydrogen atom. Maybe it was just a property of the helium, silver. But it turns out that they also made the same experiment with the hydrogen, the same observation. For practical reasons, basically. Now these operators, let's say in general alpha I, let's call them lambda I. They have some interesting properties. Let's say lambda I squared. Well, let's calculate lambda I squared. This is alpha I. No sum over I, by the way. For each I define this operator. Yeah, you see, they are just, their matrix representations have just this form. They have a single one, it's one on the diagonal, and all the other elements are zeros. Well, let's take their product, alpha I, their square. Well, this is just 1. It's just alpha I, which is nothing but lambda I. You take this operator, take its square, it's the same thing. You take lambda I multiplied with lambda j, I different than j. This is equal to alpha I, alpha j. Well, this is just 0. If you take two different ones, multiply them, it gives you 0. And you also have you can write the one identity operator in terms of these things. Now, if certain things just satisfy all these properties, that is, their square should be themselves. If you take two of them, take their product, it should be 0. And their sum should be the identity operator. These things are called the projections. So lambda I is a projection operator. Now we will be using, or at least mentioning, projection operators every now and then. Now, why are they called projection operators? Well, let's just look at a two-dimensional case, or in general. Let's say we have this state gamma made up of sum over k with certain coefficients, ak, k. This is my k. Let me act on it with my lambda I, this projection operator. This will be equal to k, ak. Lambda I is alpha I. So this is not k, this is alpha k. Alpha k. But this is nothing but Kronecker delta ik. That Kronecker delta just tells me that in that summation only the k is equal to I term survives. So this is equal to, lambda I acting on gamma. This is equal to ai alpha I. So this projection operator, when it acts on any ket, It just kills everything that is not in the, let's say, alpha I direction. And the only thing that remains is the component with the coefficient in the alpha I direction. It's just like in real space we have the corresponding analog. Let's say we have x, y, and z. You take this vector. If you want to calculate the projection on the x-axis, what you do is you just take this perpendicular, you draw a perpendicular line to the x-axis. This is the projection in the x direction. And this is basically the same thing. It does the same thing. Now, any questions up to this point? Now, for today, I will just stop here. On Wednesday, what we will do is, okay, we had identified the matrix element for SZ, but what about SX and SY? We have all these Stern-Gerlach experiments, both in the X, Y, and Z direction. So we will identify those states. What do we mean by SX plus, SX minus, SY plus, SY minus, the kets, and what about the matrices? That we will discuss on Wednesday. Yes? Well, you see, in general, when I give out the homework, you will have 1 weekend to do the homework. So if I will try to prepare it as much as possible, as early as possible, probably not today, but tomorrow, and then you will hand them in next Monday. If I distributed it after Wednesday, then it will be next Wednesday. But in the homework, you will know the deadline.